setting up the buffet now.
All right. So I put a segment together here, and again, we have clientele that would choose to eliminate all fossil fuels from a project. I understand it. I get it. We also have clientele that would say, well, if I have a boiler in the system and I'm going to add a heat pump, should I or can I heat the existing boiler as both supplemental heat and backup heat? So I'm going to try to make the case for why I feel that there are definitely some benefits to keeping that existing boiler in place. We've talked about performance of any air source heat pump. Basically, the heat pump capacity goes down as the outside temperature goes down, but the heating load goes up. And I'm sure most of you have probably seen this balance point type graph. So there's some outdoor temperature, in this case, is about maybe 26, 27 degrees, where the output heat pump equals the heating load. And if it gets colder, we need something else to meet that heating load. Now, it could be a wood stove, it could be anything, okay? But we're going to need something else to add heat to the building. If there's a boiler in place or in new construction, if someone chooses to put a boiler in with the heat pump, that can provide that supplemental heat. Okay, so it's just, that's air source heat pumps. You might say, well, should I oversize the heat pump? You can get away with oversizing an air to water heat pump. It's not the same as air to air because you have thermal mass in the system, especially with a buffer tank. We can put a 4-ton heat pump in a 3-ton building. That simulation I showed you for Plattsburgh, that was a nominal. Again, I use the word nominal because that heat pump performance is a constantly changing number based on outside temperature as well as water temperature, right? But we can put a 4-ton heat pump into a 3-ton building. And basically it's going to shift the balance point towards a lower outdoor temperature. If we put a bigger heat pump in, this red curve would shift up here like this, and it would shift towards that lower outside temperature. Okay. The boiler provides backup. Now, we were just talking during the break. There's a lot of new product coming into the market rapidly. And I looked at a lot of it. It's good stuff, but there's a lot of stuff in an air to water heat pump, as there is in a water to water heat pump, and even in an air to air system today. There's a lot of circuit boards. There's a lot of sensors in there. And the question is simply this: you're a homeowner, you've installed an air to water heat pump, something happens to it. Maybe it's as simple as a thermistor sensor, which is a $5 component, right? Fails. You're going to call the company that installed it. How quickly can they replace that component? If they have it in stock, or if the local wholesaler has it in stock, it should be as routine as a boiler nozzle replacement. Okay, but the question is, do they have it in stock? Remember, some of these products are coming in as products that are manufactured overseas, be it in Asia, or be it in Europe. And I have stressed to companies that I've done work for, it is essential that you have replacement components. Again, during the break, I'll share what I'm talking about. Some of the heat pumps actually come with internal circulators. They're built right into the monoblock heat pump. Those circulators use union connections to attach the circulator to the piping. The standard circulators in North America use flange connections. You've seen them in hydronic systems. So that's a problem. I can't replace a union connection circulator with a flange connection circulator without going in there and redoing some of the piping. To add to that, many of the European products and the Asian products use 230 volt internal line voltage wiring on the circulators. Go to an FW Web and ask them for a union circulator with a 230 volt input. It's not there. So I feel it is important to have a backup on any kind of heat pump today. And that opinion is not shared by everybody. Some people feel the heat pump alone, there's no need for the backup. Well, you're assuming what your client is willing to put up with at that point. If it's 10 below zero, and that 4-ton heat pump is putting out 1.5 tons of output, okay? You're going to have cold climate, and that's going to be a problem. So again, if there's an existing boiler, it can serve as the backup, and it can automatically come on. It doesn't necessarily require anybody to throw a switch. If it detects that that there's a load requirement, in other words, the building is calling for heat, and it's trying to get it from the heat pump, but the heat pump is off, it's going to automatically switch to the boiler. Some systems will switch based on outside air temperature. There are controls that will do that. And you actually have inputs on fuel cost and COP performance of the heat pump. They will calculate at what point it is less expensive to operate the boiler than it is to operate the heat pump. And they'll simply switch over. Okay. So having both supplemental and backup is justification for a boiler in there. Electric backup may or may not be able to provide 100%. It depends on the capacity relative to the load. You know, do you have 3 kW of backup heat? Do you have 12 kW of backup heat? Yes, you can get electric boilers that will provide 100%, but make sure that the service entrance is up to handling that. And that's the next slide. Okay. I don't know if you find many of these around. No, good. They're out there, believe me. There are buildings that are wired with 60 amp, even 100 amp services with fuses.
And pennies behind them.
What's that?
We're putting pennies behind them. Quarters, so
Yeah.
whatever it is.
So, you know, again, electric resistance, heat in particular could require an electric service upgrade. It's something you really need to take a look at. If you go in and you find a panel full of breakers and there's already, you know, obviously a lot of electrical load in the building, an electrical upgrade could cost a lot of money. Is there any incentives in Vermont for electrical service upgrades?
No, there's, what's that program?
There was a grant. There was a grant program.
Grants.
Okay.
ARPA funded grant.
Okay.
And they were like income related.
Yeah. In general, if it's new construction, single family residential, I would say 200 amp service entrance is what you want to put in. That can generally handle pretty much anything the single family house. Now, I say single family, maybe 3,000, 4,000 square feet. If you're going to do a 50,000 square foot building, that might need a 400 amp service, or we've seen buildings, residential, single family homes with 600 amp services. Pretty impressive. There's a lot of great boxes in the basement. Here's another thing, resiliency. I could run a gas boiler or even an oil boiler on a little, I call them tabletop generators like this, or little camping generators that Harbor Freights, they sell them for $600. Honda's a little more, Honda's about $1,000. But here's an idea. When you add the heat pump to the system, or even when you just install a boiler, a fossil fuel boiler system, if you can use a transfer switch to set up all the electrical feed into the boiler and the distribution system, and that way, if the heat pump if you're in a power outage and you've got one of these and you've got a few gallons of gasoline to run it for a few days, all you have to do is flip the transfer switch, and now you've got the boiler and the zone circulator or the zone valves all operating. You know, you could operate a residential hydronic system, an average one, probably less than 500 watts. And this is a 2,000 watt generator. So that's, if I'm going to use a heat pump and I want to have a full backup, I'm looking at something like this, a Generac or a Kohler generator, maybe 18 or 20 kW. You can do it, but it's a lot more expensive. And certainly if you're putting in substantial amounts of electric resistance heat. And by the way, some of the air and water heat pump systems today come with up to 9 kW of electric resistance heating built right into the unit. The Enertech unit, that was one of the Hydro splits that I showed you. That actually has 3 stages, 3 kW each, and it will stage them on as necessary. And some of the other products that are coming into the market this coming year will have electric resistance heat built right into them. But many of them don't go beyond 6 kW. And 6 kW is around 20,000 BTUs an hour. So if it's a small, well-insulated house, that's probably sufficient. If it's 10,000 square feet, it's not going to do much. Yes.
Like kilowatts do you see going to like buffer tanks? Like, a lot of like buffer tanks have like electric heating on like in them as like just in case kind of thing, like
Yep.
as like a supplemental, like a.
Usually they limit to about 6 kW. They'll have 3,000 watt elements, top and a bottom. Yeah, and I'm going to show you some systems that actually have used those for off-peak, gathering off-peak energy. So yeah, you could use tanks like that as buffer tanks, or an electric boiler as well. And electric boilers will go anywhere from, I think the small ones might be 3 kW. They'll go upwards, even single phase up to probably at least 20, maybe even 25 kW. But that, as I say, you're probably going to spend more on the wiring for a 25 kW electric boiler than you are to buy the boiler itself. Have you bought any copper cable lately?
No,
I had to buy 100 feet of 10-3. And it was $200 and something at Home Depot for a coil this big. Heck, yeah, 100 feet of 10-3 copper. Okay. The cost of removing the boiler. Okay, if the boiler is functional, and I say, this is a cast iron boiler, and there's, I'm sure you've seen many cast iron boilers. One thing I will say about cast iron boilers, they can last a long time. They're reasonably maintained. By a long time, I mean, we've seen cast iron boilers that are running that are probably close to 100 years old.
Oh, my God.
Okay, now, that's pushing it, but 20, 30 years is still, I've got 2 cast iron boilers that are both about 25 years old, and they look brand new. Every year, we change the nozzle, we clean it, new filters on it, and there's not a lot going on actually inside the boiler. This is where most of the action is, right here at the burner. But if you've got a boiler that's still functional, and you say, I'm going to remove it, well, you do have to look at the cost of removal, especially getting rid of underground tanks like this, or even this kind of a tank, getting that out. I don't know. Does anybody here have experience locally up here with removing 275 gallon? What are you finding for cost?
About $1,500.
1,500?
And then
Some crazy guy to move for free.
What's that?
I found some crazy guy to come take it out for free.
Yeah, he wants to steal, right?
Yeah.
He's gonna salvage steel. What does he do if there's 10 gallons of oil or 20 gallons of oil? Does he pump it out?
Well, they leave that in the basement. I said.
Leave that in the basement?
Yeah.
I'm sorry, you were,
I've just taken it out myself.
okay,
There's a lot of people like, there's fuel in it, it's diesel. They just put it out.
true.
Put it in their tractor or whatever, and then
Yeah.
things.
Put it in a tractor, but don't put it in the truck.
Don't put it in your truck, but you put it in a tractor, that's fine.
Everyone knows about that, right? Off-road diesel versus tax diesel.
Yeah.
The new trucks actually can detect that. I think.
No way.
Yeah, the trucks can detect if they've got non-taxable diesel.
But they can't detect when you put DEP in the wrong tank. That's interesting.
I assume that metric changes if you're pulling out, like, if it's like a natural gas boiler. So,
Well, yeah, it would. It would. But you still have some cost just associated with, disconnecting it, if nothing else, labor. Yeah, it would be definitely less than gas. Again, there are loads, and I pointed at these indirect tanks. One of the characteristics of indirect water heaters over the years, when these things were developed, they were developed around boilers. And this is a classic one. These are the connections on the coil. The coil is just in the bottom of this tank. And these coils were sized by the manufacturer, assuming anywhere from 180 to 200 degree water. These coils are not very good heat exchangers when they're brand new. Now, what happens to that coil over the years if you've got any kind of solids in your water, magnesium, calcium, that type of thing? they scale up. And when scale forms on the domestic water side of the coil, the heat transfer can go down even less. So if we take an air to water heat pump, even if it could do 140-degree water, and we just connect it to a small and potentially scaled coil, anybody know what's going to happen? Speculate.
No, it's gonna get hot water.
The heat pump is going to short cycle. The heat pump is going to produce heat at a certain rate, but the coil can't accept heat at that rate. So the temperature between the heat pump and the coil just keeps going up, and it goes up quickly, and there's an internal temperature limit in the heat pump. It just shuts the heat pump off. And if you reset it, it'll just go through the same cycle again. So you've got this thermal bottleneck based on the coil. And quite honestly, today, the North American indirect tanks, with a couple exceptions, the coils are pretty small because they were designed around them and the thought that we'll have, and look at the ratings. These are taken right out of the ratings table. First hour ratings based on coil temperatures of 180 and 200 degrees Fahrenheit. Okay. Heat pumps, just current generation heat pumps just can't get to those temperatures. So there may be logic in saying, I'm going, I don't want to tear out this and put another $2,000 into the system to get a better tank. I could set up a system where the boiler heats the tank and the heat pump does everything else. Or, and I'll get to, I could set up a system where the heat pump with a separate tank does preheat to maybe 110, 120 degrees, and then send the preheated water into the existing tank and let the boiler top it off. That's another possibility. But there are times when heat pumps just simply can't make the temperature that's necessary for the load. If you had a question.
I think it's really dumb, slowing down the flow rate.
Won't help it.
Right.
It actually makes it worse.
Yeah.
Yeah. So. Okay, now we get into good stuff here. Time of use rates. You get time of use rates. Sorta?
Not for resident.
No? Okay.
Oh, yeah.
Charging, yeah.
Oh, just for car charging.
We have a residential rate, we have a residential time of use rate, we have a similar
Okay,
for commercial, we have a special rate for charging your car.
okay. So let me ask you this, and I'm asking this, I don't work for utility. You think utilities are going to get more creative over the next few years with rate structures as a means of managing load growth? What do you folks think?
Yes. And on the utility.
Depends on utilities. That's an well, there's a couple rate structures, one from up in Ontario there and in Nebraska. And I just put them in as examples, but imagine we could coordinate operation of the heat pump and storage with time of use rate structures. And I'm going to show you a project here in a minute up in Maine that's actually a test bed for this, and they're getting some very impressive results up there. But the idea would be you would run your heat pump as much as possible on the off-peak rate and then put the surplus energy into storage. And then during periods when you have the on-peak rate, you would draw from storage and keep the heat pump off. That's the ideal scenario. And it might be a compromise. You might have to run 1 hour on on-peak rates. It all depends on storage, the load characteristics, the capacity of the heat pump, and so forth. But the ability to coordinate with on-peak and off-peak rates, especially now that you have water in the system. Remember, water is the best stuff on earth for sensible heat storage. Water is 3,500 times better than air at storing heat. So thermal storage tanks or buffer tanks, a slab with tubing in it, that's a tremendous amount of heat storage potential. So think about how all that could be coordinated with operation of an air to water heat pump. And this is just this is a concept right here. This would be solid thermal storage. And I don't want to go too far into it, but the idea would be there'd be a material, and it's probably not going to be concrete. It's going to be something called flowable film that would be in an insulated compartment, if you will, under a floor slab. And it's critical that there's insulation between the floor slab and this thermal mass, because you need to control the rate of heat release. If you just have people have asked me, can I just do a 12-inch thick concrete floor, put tubing in it? And, charge it up on off-peak rate. You can do that, but you don't have control on how that heat is coming out. Suppose the sun starts coming through the windows, or you throw a party and you've got 50 people in your house. That's immediate internal heat gain, and you can't just stop that slab from releasing heat. But with some kind of a thermal barrier in between, you have some degree of control. And again, I don't want to get into the details, but that's a hydronic system that would be capable of sending heat from the heat pump into this during off-peak rates, and then extracting heat from this and putting it into some kind of a heat emitter system in the building. I think this is really one of the major frontiers going forward for hydronics, is the combination of time of use rate structures of some form, as well as combination with heat pumps and thermal storage. And leads me to this. This is a project up in Millinocket, Maine. Anybody ever hear of Millinocket? It's a pretty interesting place. They had two great big paper mills up there, which are both gone at this point. And Millinocket, the local Central Maine Power, I believe is the utility up there. At times, this Millinocket area, because of wind farms as well as hydro generation, there are times when they're generating more than what their local grid requires. So they're looking to offload that power at the wholesale level. And they do it through pricing structures. Again, at wholesale level. These are not price structures that are available, at least at the present, to retail customers. They put out 48-hour in advance pricing structure. So every hour, this is the wholesale price for each hour for the next 48 hours. And then other utilities can decide, I'm going to buy so much at this hour or whatever. And at times that wholesale price actually goes negative. Okay, and I never heard of that before. Negative utility rates at the wholesale level. So imagine if those kind of rate structures at some point in the future could be available at the residential level, where you would have extremely low cost electricity, if not negative pricing. And what you're looking at here, basically, those are 119 gallon tanks. They do have elements in them that right now, I don't believe they're using the elements, but these are the thermal storage tanks. And I'll show you the heat pump in a minute, but this is a hydronic system. And this thing is actually being run by this little board right here. It's called a Raspberry Pi microcomputer. It's about a $40 computer. Anybody ever heard of that? Maybe your kids work with it in school. It's a self-contained computer, and it is actually, they can simulate rate structures and with software and actually run these systems. And I've been up there to see these systems. I've actually worked with them to help work out some of the piping design on this. And these are not in passive houses. These are not in net zero houses. These are in houses that were probably built in the 1950s, bungalows, nothing exceptional. And the performance, I think I've got some of the performance, here's one of the houses here. Again, this is all, recorded performance, but there actually are times in the winter when it was 5 degrees below zero. And the house was completely heated by thermal storage without running the heat pump. So they are currently working on more demonstration systems. Efficiency Maine is one of the sponsors of the projects up there. But again, I got pulled into this project a couple of years ago, and I've just been super impressed by what I've seen up there so far, and very encouraged about the potential to bring heat pumps, thermal storage, and time of use rate structures together. Okay. Actually, we proposed to do a session at the Better Buildings Design this spring. I haven't heard whether we've been accepted yet or not, but George Baker from GridWorks and forget it, we're going to present this in a lot more detail.
Some question.
Yes.
Would that, a large amount of thermal storage, would that really increase the efficiency of an air to water heat system as well? Like, could you heat up your storage water when it's like not quite as cold? outside, like say like you're looking for like super cold temperatures, like, oh, it's sunny during the day and it's 20 degrees.
That's possible.
Efficiency, then like, oh, now it's gonna be 10 below at midnight.
Yep.
Like rather than time of use.
Yep,
rate.
that goes in, actually goes in, that goes into the algorithm. They're looking at advanced weather forecasting data as well as, over time, you can deduce what the heating loads are by recording what the heating loads have been previously compared to air temperatures. So you can project forward what the heating load is, and you can also project forward on ambient temperatures and what the heat pump performance would be. This is, the math is pretty complicated on
And
it.
that's the little Raspberry Pi controllers sort of.
The Raspberry Pi is what's executing the code, but the joules are in the code itself.
Yeah.
And by the way, that code is all open source. That the people that are doing that want to push this out. You can check it out if you want to see the people that are doing this. Gridworks.com or gridworksconsulting.com. George Baker, Jessica Millar, fascinating people. And they're also working with Ridgeline Energy Analytics on some of this, and Efficiency Maine is supporting the work. So, okay, what time we got left? I want to show you piping the boiler up with the heat pump. Okay.
John, may I ask a quick,
Sure.
a question? Maybe, I don't know if it's, maybe not quick, but if we can't get to it now, I'd love to address it at some point. But you showed a slide. We have these dual fuel systems. So we're keeping the boiler, we're adding an air to water heat pump.
Mhm.
And we talked about a balance point. And when the heat pump can't carry the load, then the boiler can come on. That's one scenario. There's also the scenario of, so that would be like a capacity balance point. Right?
Supplemental heat.
Yeah. So there's also like a scenario where it's like a economic balance point.
Mhm. Yep.
And at some point, it's cheaper to heat the home off of the gas boiler. At some point, it's
It could be.
cheaper to heat the home from the heat pump. And I'd be intrigued if, like, we're asking people to explore this, like, we've got to show if we can show that there's a cost savings to condition their home with this system, that could also provide cooling, right? I think that would certainly help to sell.
Yeah, and to find that point, that economic balance point, you would need to know the COP of the heat pump as a function of outdoor temperature.
Yeah.
And the capacity as well, and what the competing fuel prices are.
Yeah.
And then you could make a calculation. What's the lowest cost per million BTUs? Is it the heat pump? Is it the boiler? And then determine when that switchover is going to occur. And that's not necessarily a fixed temperature. That could vary depending on the performance of the heat pump. As your air temperature goes down, your COP is going down.
Yeah.
But that could be done. In fact, there are companies in Europe that sell controls that you input that information and that controller will make the switch for you. So, and some of the heat pumps, again, there's one product that is likely to be on the market next year that has that as an internal function. It's built right into the firmware. So if there is a boiler in the system, it has the contacts to initiate the boiler, and it can do the calculation based on the economic balance point. So, yeah, controls can do a lot.
Thank you.
Heat pumps. Bottom line on piping boilers with heat pumps, you pipe them in parallel, not in series. There's really very, very few times when it's ever a good idea to put multiple hydronic heat sources in series with each other. By series, I mean you go into heat source A, you come out, then you go into heat source B, and then you go back to the system. There's a lot of downsides to that. So this shows, let me actually start with this one down here. This is a modulating condensing, or what we call a mod-con boiler. Typical wall-hung gas-fired, could operate on propane as well. And it's got its own circulator with a check valve. That circulator would come on. The boiler actually turns on the circulator. So here's the cool water coming back from the system. And if the boiler was the sole heat source, the flow would be up through the boiler and back to the system. Okay. If the heat pump were the sole heat source, the cool water would come back. The heat pump is running its own circulator here. So that pumps the water through the heat pump up, out to the system. So either heat source could operate as the sole heat source, or they can operate together. Okay, and What determines when they operate together? It could be a number of things. It could be the heat pump doesn't have enough capacity if it's extremely cold out. And many of the heat pumps have that control logic built right in. They can fire the boiler when necessary. Right? If you're using what we call a conventional boiler, that would be cast iron, steel, or copper tube boiler. The term conventional boiler means a boiler that is not intended to operate with sustained flue gas condensation. Right? When you started your car this morning, if your car was parked outside, did you see water dripping out of the tailpipe as it was warming up? You ever see that? Where'd the water come from? Combustion, very good. When you burn a hydrocarbon fuel, you produce water vapor as one of the byproducts. As that water vapor goes out through the exhaust system, it condenses into a liquid. That's what you see dripping out the tailpipe. These boilers were not designed to let that reaction happen inside the boiler. They'll scale up the heat exchanger. I showed you the vent connector that was rusted out. So what's necessary, you don't have to throw the boiler away, but you do want to install what's called an anti-condensation mixing valve. And it's a very simple device. It's a thermostatic valve. And what it will do is it's going to measure the temperature of the water coming back from the distribution system. If this is below about 130 degrees, it's actually going to block that water off, and this pump is going to be on. The water's going to do this as the boiler warms up. Now, that's only going to take 3 or 4 minutes if the boiler was at room temperature. And as the boiler starts to warm up, this valve is going to sense that, and it's going to start opening the cool port. And that as we open the cool port, that's going to allow some flow to go up through here and out to the system. So what it does is it allows the boiler to warm up in kind of a minimal water volume mass. Okay, this might only have a gallon or 2 of water. Now the boiler itself, if it's cast iron, that could have 6, 8, maybe even 10 gallons of water, but it's still a small amount of water compared to what the mass is out here. So it is designed to protect the boiler from sustained flue gas condensation. This is important if you're retrofitting. There are other ways to do this with motorized mixing valves, but the reason I stress that it's important, you may have a distribution system that's operated at relatively high water temperatures for years and everything's been fine. You're adding the heat pump, and now you might choose to use outdoor reset control on the system. That's going to lower those water temperatures under partial load conditions. And we've seen this happen. The boiler that's operated fine for 10 or 15 years, all of a sudden, now it's being exposed to these lower water temperatures. And if it gets below 130, you're going to start to generate condensate inside the boiler. This boiler loves that. But this is made out of a high grade of stainless steel heat exchanger. This is cast iron. Okay. This is vented through very high grade stainless or other polypropylene materials that can handle the condensate. This is vented through galvanized steel pipe, and it's going to corrode. So if you're retrofitting or if you're installing a conventional, like an oil-fired cast iron boiler, you need an anti-condensation valve to protect it. So again, I'm not gonna talk about each one of these because PDF file for the slides. Did that go out or
Not yet.
not yet? There's a PDF file that I sent up to, and that'll go out to everybody. So you can read about it later. But basically, I've talked about most of this stuff on here. Okay. I come in parallel. I like to use magnetic Gert filters. There's several on the market now. This will collect what's called magnetite. That's basically very, very fine particles of iron oxide. If you've got cast iron radiators or steel pipe or cast iron circulators in the system, there's a chance you're going to have some residual magnetite in the system. And you don't want that inside the heat pump. It just coats the surfaces of the heat exchanger. The other thing is many of the circulators today have gone from what's called a permanent split capacitor motor to an ECM motor. An ECM motor has a permanent magnet, very strong permanent magnet in the rotor of the circulator. And a very strong permanent magnet loves to attract magnetite. And it can, over time, it can jam up the circulator. So especially in a retrofit, we like to specify a magnetic dirt separator. And, this is a residential scale system, but there are products like that for very, very large commercial and industrial systems as well. I just want to stress the circulator in each one of these. A little hard to see it, but right there is a check valve, and right there is a check valve. It's important when you have two circulators like that and they're in parallel piping branches. Each has to have either an internal circulator built into the loop of the circulator or an external check valve. Anybody know what'll happen if those check valves aren't there? Let's say one circulator's on and the other one's off. Yep, you go backwards through the circulator that's off. A standard circulator without a check valve, water can flow through it either direction. And basically what'll happen, instead of all your flow going out to your load, some of it is going to go in reverse through the inactive circulator. So many of the small circulators today come with the little plastic check valves. If you have a circulator that doesn't have that, you can use an external spring-loaded check valve. Okay. Here's another possibility where you're using what's called primary secondary piping, and that ties each heat source in with a pair of closely spaced T's. What these closely spaced T's do is they decouple the pressure dynamics that this circulator is creating from this circulator, as well as from out here. There's going to be at least one other circulator. So we call that hydraulic separation. When would you use this? If it simplifies the modification of the system piping. If you've got existing piping and you're trying to do what I call the least invasive surgery on that piping as you add the heat pump, this is an acceptable way to try to minimize that modification of the piping. And these points are basically all the same here. As see the land on what's there. There we go. Okay. It's the same thing. Each circulator needs its own check valve. Literally put the T's right next to each other, put the magnetic dirt separator in the system. Right. Again, this is what happens when you run a conventional boiler at conditions that allow sustained flue gas condensation. That's an example of one of those thermostatic anti-condensation valves. Caleffi makes them, Danfoss makes them. They're readily available on the market. And there's no electricity. These are just thermostatic elements that are in here. Now, there are some companies that are promoting what's called direct to load piping. There's no buffer tank in the system. They're doing that because they have a wide range of speed control on the compressor out here. The idea is this. You can do zoning out here if you want, turn zones on and off, and the heat pump will sense when that happens. And it senses it based on temperature rise. For example, if I just turn several zones on, I'm going to have a cooler stream of water coming back initially. And inside the heat pump, it's measuring supply temperature and return temperature. If it all of a sudden sees that delta T open up, it's going to increase the speed of the compressor and vice versa. The benefit of this is that there's no buffer tank. And one of the companies, and it's Enertech Global, if you check out their hardware, they stress that their heat pump does not require a buffer tank. I've challenged them a little bit on that, by the way, and I've said, well, what if you just hook up a towel warmer to it? So it can run with just a towel warmer.
So in that situation, glycol is going directly to the emitters?
Yep. Yep. This would be typically in a climate like this, about a 30% solution of propylene glycol in water. That's about all you need. You don't, I've seen misuse of antifreeze. You don't need 50%, even 40% in a climate like this.
That system needs sort of recharging. Like, would you have to be like, I know because like boilers have like fill it for lost water.
Yeah, typically you put in what's called a fluid feeder. there's a company called Axiom. And Axiom, they make these little 5-gallon plastic containers, and you put the mixture of 30% glycol water in there. And there's a little gear pump and a pressure sensor. And if it senses any drop in pressure out here, it just turns on that little pump and adds some fluid to the system. You would not hook up an automatic makeup water system.
Right.
Correct. If you had a leakage, you'd over time you would dilute it. Now, I put down some points on this. This is possible with a wide range of compressor speed control, no buffer tank or a hydraulic separator. In other words, if you look at that schematic, whenever there's a load out here, whenever there's a flow out here, it's going through that heat pump. There's no way I could have flow out here and not have it go through the heat pump. And that's okay under certain circumstances, specifically when the heat pump's very close to the building. Okay, if you're putting the heat pump a couple feet outside the building and you're insulating this piping, okay, yes, you're going to have a little heat loss. I'll give you the scenario. Let's say the heat pump is off for whatever reason, okay? And the boiler is on, the boiler's injecting heat right here. This circulator is on. This flow is, this warm water that's coming back from the distribution system is still going through the heat pump. So there's going to be some heat loss there. Can you control that heat loss? Yeah, to a degree. Short pipe lengths, good pipe insulation. If you're running the system on outside reset control, that'll minimize that water temperature. Under those conditions, I think this is acceptable. But how about if somebody says, I don't want to look at this behind my house. I want it 100 feet away behind a fence.
Time to go underground.
Well, yeah, and even underground, you're going to have losses though. So,
And is that PRV there just because we can't have it on the home block heat pump?
that PRV is there in case that flange and that flange gets closed off, so the pump gets turned on.
Gotcha.
And I'm glad you mentioned PRV. It's essential when you have a closed hydronic loop of any sort with a heat source in it, that there's a pressure relief valve in that loop. I just had some interaction with a heat pump that literally blew apart inside because the electric elements were on. A valve that was supposed to be open didn't open, and there was no pressure relief valve in the system. And it finally blew apart the lowest rated component, and it just filled the basement up with steam.
I guess what's interesting, John, is you were saying like with the monoblocks, a lot of the proprietary controls are in there, but they couldn't really have a pressure relief valve because if it was zero out and the thing blew, it would just freeze in place. It
Well-
wouldn't actually discharge.
Yeah. The pressure relief valve would typically be inside. And some of the products, some of the, like the hydro splits, as well as the DX split systems, they'll put the pressure relief valve
Is that
inside.
inside?
It's inside, yep.
Just like a boiler.
Yep. But this whole system would have to operate on a solution of propylene glycol water. Now, if you're gonna move the heat pump a distance away, I did a different schematic for it. What I'm doing now, I'm putting a couple motorized valves in. Okay, and what would happen is now, if the heat pump is out of service, this valve would close, this valve would be open. Now the flow is just doing this. So if the heat pump is running, this valve would open. That, I feel, is more appropriate when the heat pump's going to be a fair distance away from the building. Because again, we don't want to lose a lot of heat outside.
What's controlling those valves in that sense? You have like the,
Whatever is calling the heat pump to operate, whatever contact closure you're using to call the heat pump to operate, you could,
control those valves.
correct. So this has to be open if this is on, this has to open if that is on. And it depends on the valve too. You can get motorized valves that are motor open, spring close. So you give them power and they open, remove power and they close. Other valves, they power open and then they also power close. So depending on what the valve electrical requirement is, you might have to use a relay or something, but the bottom line from a control design standpoint is that's on, that valve's gotta be open. In fact, all the monoblock heat pumps have flow sensors. And when a monoblock starts up, the first thing that turns on is the circulator, and it might run for a couple minutes before the compressor turns on. It's doing that to verify that there's stable and adequate flow through the heat pump. Because you don't want to turn on the refrigeration cycle if, let's say, the pump failed. This is telling the heat pump, the pump is working, I have adequate flow, I can start the compressor. So that's another approach. Now, we got time, I'll run through these system examples. All right, let's start with this. This very common, you've got a boiler, conventional boiler, let's say it's a cast iron boiler, oil fired, and we've got 3 zone pumps on it and some fin tube. So we want to add an air to water heat pump to that. So here's one way we could do that. What I've tried to do, if you look, kind of study back and forth, I've tried to preserve as much of this as I can. In other words, I don't want to take that whole header apart and reposition all those circulators if I don't have to. So if I can kind of cut it here and cut it here, move the boiler and then reconnect that, and you can see I've tied this with a pair of closely spaced tees. Now what this does, again, this is called hydraulic separation. What it does is it prevents these circulators from interacting with these circulators. Okay, again, if we had more time, we could get into it, but it's important when you have multiple circulators in a system that they don't conflict with each other. Okay, and I use the idea of bullies on a playground. You've got a big bully and a little puny person, and they're gonna, if they see each other, they're gonna fight. Guess who wins? The big one. Okay, so if you have large circulators and small circulators and you don't have them hydraulically separated, the large one can dominate. It can actually stop flow completely, even though the small circulator is running. It will prevent flow from actually moving through it. So if you look at what's going on here, the heat pump and the boiler are piped in parallel. In other words, the common fluid returning, it could go into the boiler, or it could go into the heat pump, or it could do both at the same time. So the boilers are in parallel with each other. There is a check valve in each of the circulators, so we don't get reverse flow. I also put purging valves on each one of them, and this would be an isolation flange. If I feel it's important that if you have a component, be it an air to water heat pump or a boiler, there's a possibility you might have to remove that at some point for service or replacement. So you should be able to close off valving so that, for example, if I had to remove the heat pump, I don't have to drain the entire system. I can keep the boiler operating, keep heat in the building. If I had to remove it, or maybe I have to replace this hose here. Right, so I could shut off that ball valve. I could shut off the ball valve inside the isolation flange. And again, you see there's the pressure relief valve. Never set it up so the pressure relief valve is isolated from the heat source. Always make sure it can communicate. Same with the expansion tank. Make sure the expansion tank is always connected into the system so both heat sources can feel its presence there. So that's the modification of it. And I put down entire system operates with 30% solution of propylene glycol. And I also put down small zone, not less than 20% of minimum output of heat pump, otherwise use buffer tank. Variable speed heat pumps can go down to roughly about 25% of the rated capacity. So as the zones are turning on and off, that heat pump would adjust its compressor speed, just the way a modulating boiler will adjust its burner operation. But if you have what I call micro zones, what's a micro zone? A towel warmer in a bathroom has a separate zone. That might need 500 BTUs per hour. The heat pump simply can't go down to that capacity. So if you've got a lot of zoning going on, what I would do is replace this right here with a buffer tank. These 2 pipes would come in and out of the buffer tank. These 2 pipes would come in and out of the other side of the buffer tank. Now the buffer tank will provide the hydraulic separation for the circulators. but it also adds enough mass to the system. So the heat pump isn't going to short cycle. Do another one. Here's a modulated condensing boiler doing some floor heating. This is a hydraulic separator. Basically what a hydraulic separator does is it separates the pressure dynamics of that circulator from that, but it also serves as the air eliminator for the system and the dirt eliminator. So dirt will be captured down at the bottom. And the newest versions of these have magnets down here. Magnetic dirt separation has become much, much more popular in the hydronics market over the last 5 years. And I think it will continue to grow. And the reason is ECM circulators. Most of the companies now, Taco, Grundfos, Armstrong, Elo, most of those companies that are selling the residential circulators have pretty much moved over to ECM. Now they haven't eliminated their standard circulators yet. That's coming in May of 2028, I believe. There is a DOE mandate, can't tell you the number of it, but I believe as of May 2028, no longer can manufacturers sell permanent split capacitor motor circulators. The standard, do you all know what a Taco 007 is? That little green circulator you see in all these hydronic systems? I mean, it's like, if there was ever a hydronics museum, the Taco 007 should be in that museum. It is the most ubiquitous circulator. There's millions of them out there. But the wire to water efficiency on that circulator is probably between 15 and 20%. And that is not just because it's a Taco circulator. The wire to water efficiency of a Grundfos equivalent would be right about the same spot. They aren't very efficient at converting electricity into kinetic mechanical energy to push fluid through a circuit. But ECM technology, the variable speed permanent magnet circulators are becoming more and more dominant in the market. And a magnet in the bottom of the hydraulic separator will catch magnetite, and that prevents it from collecting in the circulator, or for that matter, in the boiler or anywhere else in the system. So we're going to convert that over to this. Okay. Now I'll ask you some questions. Is the heat pump in parallel with the boiler? From what we've talked about. Yes, very good. You thought it was a trick question. Now, it is. It's basically very similar to the other system, except we now put a hydraulic separator in here. And if you go back to the other schematic, in fact, let me do that back. Here's the magnetic dirt separator as a separate component. Here's the air separator as a separate component. When we go to this, the air separation is done by this, as is the dirt separation. Okay. And the main function of hydraulic separation, for example, one of the things we could do, we could run continuous circulation out here. That works really good in garage type buildings. If you're going to do a system like this into, let's say, a fire station, where you have a slab and you have large overhead doors, oftentimes the thermal break is non-existent, where the slab goes out under the door out into a ramp. Ideally, there'd be a nice piece of insulation there, but that's a hard detail, especially in a commercial garage, because that's a high stress area, the slab. So oftentimes you'll find that the slab just inside those overhead doors gets cold if you stop the flow. And if the flow's off for several hours and it's extremely cold out and it's just water in the system, what do you think can happen to the tube that's right next to that door? It freezes. So in those systems, some designers will opt to have that circulator run continuously. And what that does is I call it stirring the BTUs in the slab. It'll pick up heat in the core of the slab and move it to those cold spots under or near those overhead doors. We could run this continuously out here And then we could use the heat pump, and you see, I haven't shown a sensor back to here, but we could use the heat pump to monitor this temperature and simply inject heat into that circulating loop as necessary based on outside reset control to maintain the building at whatever set point we want. And the same for the boiler. So again, it's not complicated. You put the two heat sources in parallel. Each has its own circulator. There's a pressure relief valve, expansion tank. Pretty straightforward. Okay, now we'll get a little more messy here. Here's another residential system, 2 zones of baseboard and an indirect water heater and an oil-fired conventional boiler. And by the way, when I show you the makeover, that's just one option. There's probably half a dozen acceptable alternative piping layouts that you could use. I just want to show you examples that are using the concepts we talked about earlier. Okay, so here's one. This requires a little bit more rearrangement. I'm trying to minimize the disruption of the piping out here. So remember, one of the concepts I showed you earlier was instead of putting the 2 heat sources, the heat pump and the boiler in parallel, we could connect each using a set of closely spaced T's to a common loop that then goes out and serves all those loads. If you do this, it is important that the heat pump is the upstream connection. In other words, I do not want to do this. I don't want the boiler upstream of the heat pump. Anybody know why? Think about heat pump performance as a function of water temperature. We want the coolest water into the heat pump, right? So if both of those were operating and if the boiler was down here, it would raise the temperature of the water before the heat pump, which would be up here, even sees it. It would still work, but it's definitely going to be less efficient. So always think, where can I access the lowest water temperature in the system and use that water temperature for the heat pump? Has anybody ever done injection mixing on gradient up here? I don't know. Some of you are installers, right? This is what's called a variable speed injection system. Basically, think about it this way. We've got a loop down here with a circulator. So we've got water spinning around here, delivering whatever we load onto it. We've got a boiler up here in another loop. This is generating heat. So this is the bridge between where the heat's being created and where the heat needs to go. And by controlling the speed of that circulator, we can, if that circulator is off, there'll be 0 heat transfer across here. And the reason is the closest spaced T's. Okay? But as we start to increase the speed of the circulator, we start injecting hot water. And that mixes with some of the cool water coming back around through here. So we got these 2 streams coming together in this T. And depending on how fast the hot water is being injected relative to this flow rate, we can control the water temperature going to the load, to the heat emitters. There's thousands of systems in North America that are using this kind of setup. This is a way to do low temperature floor heating with a conventional boiler without requiring a mixing valve, like a 3-way or a 4-way mixing valve. We've designed many systems around this. So let's say you've got this, you run into this in the field and you want to add the heat pump to it. Okay, so start over on the right side. I've left this whole thing intact. Haven't started to cut pipes here, but right here, I've put in a pair of closely spaced T's. And just to mix things up as far as the heat pump, I'm showing a split system, a DX refrigerant split system. So this would be a refrigerant tube here. This would not have to have antifreeze. It still could put antifreeze in if you want, but it doesn't require it because there's no water coming out to the heat pump. So it's, again, minimally invasive way to tap the new heat source into the existing piping And again, you'll see the heat pump is tapped in upstream of the boiler. And we've left as much of the piping, existing piping in place as possible. Okay. And again, you could generate 100 different possibilities easily for what you might find in the field. I've tried to pick some that are somewhat common, and I've tried to apply what we talked about earlier with either parallel piping of the heat pump and the boiler or the closely spaced T's. Okay. Let's see, direct to load. This is basically an Enertech schematic there. This is the system without the buffer tank. This is a hydro split. So what Enertech sells is a monoblock heat pump with this indoor box, and the installer basically just connects piping between the indoor box and the outdoor unit. They tap the boiler in with a pair of closely spaced T's. Again, this would have flow going through it whenever the load is active. And the only, well, I've shown this supplemental circulator. There are cases where this might be required, but cover that up for the time being. There's another circulator in this box. And if you take this one away, the circulator that's in the box, well, there is a circulator on the boiler too. But this, the same circulator that's in the box is pushing flow through here, is also pushing flow through the distribution system. It's an interesting idea. I think it will work in many applications. I still think there are applications where a buffer tank makes sense. And I give an example. We did a house 2 years ago, parsonage at our church, actually. It's got 10 panel radiators. In fact, the panel radiators came from right down the road here, Lyson. Okay. And it's got a 4-ton air-to-water heat pump in it. It's got a buffer tank. Each of those panel radiators has a thermostatic valve on it. Are y'all familiar with those? Non-electric. In fact, we used to call them non-electric, but we came up with a much sexier term for that. These were wireless thermostatic radiators. This was the original wireless zoning, long before anybody at smart thermostat company, came up with it. They work beautifully. They're simple. There's no batteries. There's no apps. There's no wires. You just set it and it just modulates the flow. We run that entire system on a single Takeo 0018 at full speed. It draws 44 watts. Partial load, it's running on about 25 watts, delivering about 36. Well, the design load is 36,000 BTUs per hour. But we have every one of those radiators is a zone because it has a separate valve on it. So that's where we put the buffer tank in. The one Achilles heel with this, this needs something to tell it to turn on, to turn the compressor on. And normally, if you have zone valves, they have an end switch, and the end switch closes when the zone valve opens. And that end switch closure is the signal, hey, something's calling for heat, turn on the heat pump. But with thermostatic valves, you don't have end switches. So that's one drawback with that. You could come up with other scenarios. For example, you could enable the heat pump to operate if it's below 50 degrees outside. Or you could have a master thermostat somewhere in the house. When it calls for heat, it enables the whole system to operate, and the thermostatic valves just act as like trim controls on that. But anyway, that's a direct to load scenario. Here's an example where we're taking basically what's called a split series distribution system. Some of the old hydronic systems, what they would do is come out of the boiler and then they have a split. And one loop would go around one side of the house and the other loop would go around the other side. Then they come back together. So what we're going to do is convert that. The modifications are listed over there on the right. So let's say we're going to add a variable speed air-to-water heat pump. We're going to convert from single to 4 zones. This is all a single zone system. Some thermostat somewhere in the house, one thermostat turns that circulator on and enables the boiler to fire. But let's say the owner wants to go to 4 zones. And the owner wants to use electric or electronic thermostats. Okay. Says we'll use high output fin tube baseboard for supplemental emitters. Let's say we've made a decision based on water temperature and COP we need to add some supplemental heat emitters to the system, okay? So here's what we're gonna do. Here's our original system. This is the surgery, after the surgery. What we've done is we've made cuts in certain spots in the copper piping where we can access the copper piping. And so, for example, this is still the original baseboard with the copper tube in it. The orange would represent the supplemental emitter that we decided to add, okay? So we're converting from copper over to 1/2-inch PEX tubing. And you might say, well, gee, that's 3/4 inch copper, you're converting it to 1/2-inch PEX. But remember now, we're creating 4 independent parallel circuits. We can do that. That will work just fine with 1/2-inch PEX. And then we put in a manifold, just like they use for floor heating. And some of the manifolds can be equipped with what are called manifold valve actuators. These are little 24-volt motors that open and close the valve. It's built into each circuit position in the manifold. And this is just a standard relay controller. Takeo makes some, Colepi makes some, a lot of Honeywell makes them. And then they all go up to thermostats. So what we've got now on this distribution system is 4 independent zones, all controlled by electronic thermostats. And this controller would have an output so that when any zone thermostat calls for heat, it can close a relay contact, which can trigger a heat source to operate. So I haven't even put the heat pump into the picture yet. I'm just saying, let's see this, put it on the operating table, convert it over to this. I should mention, one of the reasons the 1/2-inch PEX tubing is used, it's a lot easier to run that tubing around the building than it is to try to do it with copper. Okay, could I put it all together with copper? I could, but it'd be pretty expensive to do that. Okay. 2 more slides here. So I've added the heat pump, connected in parallel with the boiler, same piping details. I'm going to put a hydraulic separator in. It's going to do air separation, dirt separation, and it's going to separate the pressure dynamics of these circulators over here from whatever this distribution system is. So there it is put together. Okay. There are, and this phrase is probably overused, but there literally are endless possibilities for how you could modify an existing system. You walk into a project, one of the things I'm going to look at is how efficient is the building envelope. If the building envelope is lousy, that's where the money should be spent, folks. Get the load down, whatever's reasonable and practical, leverage programs that are in place to help with that. And then once we know what that reduced load is going to be, I'm going to look at the distribution system and say, can I start to make some strategic cuts? If I can't access any of the piping, maybe I've got to do a better job on the thermal envelope because I'm not going to be able to add heat emitters to the system. If I can access the piping, the next question is, where can I put those extra heat emitters? I can't put a 10-foot piece of baseboard in a wall that's only 4 feet long. Think about kitchens and bathrooms in particular. We often don't have wall space for that. So if I can't use baseboard, what else could I use? Panel rack, fan coil. Okay, maybe I can do some underfloor heat. There's a lot of possibilities there. But the fin tube vertical, not very funky. You can get some Runtal radiators that are vertical tubes that go up and down, and they look nice. But every one of them, there is no canned answer that you always do this. You have to go in and look at what have I been given to start with. Use the idea that load reduction is a possibility, and so is potentially adding heat emitters. And if I'm going to add heat emitters, where am I going to put them? What kind of space requirements? How am I going to reconnect the piping? But ultimately come back to a heat pump and a boiler that are now in parallel. And by the way, remember this, the anti-condensation valve? You're not going to find it on those existing systems. I'd be extremely surprised to find an existing system with an anti-condensation valve, but if you're gonna retrofit the heat pump and potentially run that system at reduced water temperatures to benefit the performance of the heat pump, you really need that anti-condensation valve.
Particularly new, like sidewall vented boilers.
No, if it's a modulating condensing boiler,
Yeah.
absolutely no. That'd be the worst thing you could do, actually. You want it to condense. But again, many of those heat pump retrofit projects, you're probably gonna find cast iron boilers with burners, oil burners.
Are there more slides with more scenarios or just?
I think we're almost done here.
Good.
Oh, one last slide. I've already mentioned this. R290, there's the global warming numbers right there. So this is what's driving. But this is also what's opposing. You've got companies out there like DuPont, Chemours that make millions of dollars a year selling other hydrocarbon refrigerants. So I think it's inevitable. I think it'll happen. My guess is you're going to see California as being one of the first places where R290 is approved. And once that happens, I think it will spread through.
People ever move to propane?
What's that?
People ever move to propane? I mean, is propane is what the 290 is?
Yes. Yeah, R290 is propane, but not the propane in your barbecue. It's the same base chemical. It doesn't have the odor in it. It's propane as a refrigerant.
But it would just be, in this situation, it would be outside.
Correct.
That refrigerant.
I don't think we'll ever see it. Well, I shouldn't say ever. Well, R290 in a mini split. You can make the point that we have propane piping in buildings now, right? Lots of it, trap pipe and everything. To make that point, whether it'll be approved as a refrigerant through like a VRF system or a mini split, I would feel more comfortable certainly as it keeping all the propane outside. Yeah, right.
So back to maybe it's one of those scenarios. I mean, we have, like, cooling is a requirement. Like now, I mean, talk to so many people, they want
Mhm.
cooling, they want cooling out of their heat pump, maybe even more than they want heating out of their heat pump.
Yep.
So
Yep.
how do we do cooling?
Okay, that's a good question. You could actually tie in. You're gonna need any of this for cooling. I could tie in here and here, go up to an air handler. Okay. I could put a valve in, either a manual changeover valve or an motorized valve. But basically, I'm making the assumption that this circulator is sized so it can create the flow through this loop as well as what the resistance of the air handler is. Now, if that is the case, then I could tee in here and I could tee in here, and I could simply take chilled water supply and return up to a coil and an air handler. I would want to make sure though that I would have some kind of check valves in here or some kind of valving so that I don't let cool water migrate out here.
Yeah.
Well, anybody come up with, why don't I want chilled water migrating out here? Let's say it's summer, it's 90 degrees outside. Cool
Condensation.
water can go anywhere to cool the house down.
Because it'll condense in those emitters.
That's the problem. Okay. And
But John, if we have 4 zones of heating, we're gonna need more than one fan coil, right?
not necessarily. Well, fan coil, yes. Air handler. I would,
Oh,
I-
okay.
I'll tell you what I'd like personally. I'd like
So one
multi,
air handler could do the whole.
the whole house.
I got you.
I like the idea of multi-zone heating, single zone cooling
Okay,
for reasonable single family houses. When I say reasonable, 3,000, 4,000, you got a 10,000 square foot house.
no, I mean,
You know,
the average.
It's sprawling. You need multiple air handlers for that. But for the average house, I'd like a single. And I'll try to justify that. When you put in several fan coil units with condensate drain pans, and you're going to use them for zone cooling, each one of them's got to have an insulated supply and return pipe. So if it's copper or if it's PEX, it's all got to be insulated because anything with chilled water in it's got to have insulation or it's going to drip. So I've got the supply and return with insulation. I've got to have condensate drain for every one of those units. You could go outside, or you might be able, depending on what your code is, you might be able to tap it into your venting, your DWV venting system. So now I've got supply, return, insulated, condensate drain. I've got to have electrical power to each one of them.
It's not sounding like it's good for a retrofit.
It's possible, but it's expensive. A fan coil with a good fan coil with a condensate drain, nominal $1,000, $900,000. Okay. It's getting all that infrastructure to it, that insulated PEX, the power, the condensate drain. So
What level of insulation do you need on those PEX slugs?
half-inch foam, half-inch elastomeric foam, Armaflex or something like that. That's fine. Yeah. If you were in a greenhouse, you had super high humidity, something like that, you might go to 3/4 inch, but half-inch is fine for condensation control. Right now, the challenge in the industry is trying to insulate components like air separators and circulators. Some companies have shells, clam shells that go over the flue of the circulator. I'm trying to get more of those into the industry. And things like a good example would be Webstone isolation flanges. You know, those yellow handles you see on the circulators on either side.
Yeah.
What will happen, even with one season, is the zinc plated steel hardware, it will start to corrode. That zinc plating just won't hold up
From the chilled water.
from the condensate, from the chilled water. Now, I'll share you a trade secret that I thought was ingenious. I just found out about it last year. It's from an old contractor. What he does is first of all, he takes the handles off those isolation valves, because you only need the handle if you're going to shut off the valve. Put a nail in the wall and hang the handle. So now the handle's out of the picture. And he takes Vaseline and he puts a thin coating of Vaseline on anything that's steel on the valve. And that Vaseline is enough to isolate the moisture in the air from the surface of that metal. Might get a little greasy or sticky, but it does the job. So coat your steel with don't gob it on there, just a little film, just enough to break contact between the moisture in the air and the surface of the component. So,
In this scenario, the whole system is glycol.
yes, in this scenario, the whole system would be glycol.
So then the fan coil units would be.
Yeah,
your-
they would be glycol as well. It won't, that's not a problem, but I tell you, it's actually a benefit if you're doing an air handler, especially if the air handler's in the attic.
You're talking and have like essentially distributed air conditioning.
Yep, yeah, a coil, a blower, and a cabinet.
Yeah.
With ducting.
Right.
With ducting.
Like flex stuffing.
Oh, I hate it. Yeah, flex ducting.
I mean, that's how you see it.
Yeah, it's,
This thing, air handler duct work, and you're like, I actually want to get cooling into the situation.
Yeah.
It almost seems easier to run piping. and
Well,
chiller heads.
it might be. You got to look at
And
it.
as a builder, it's hard to get duct work.
Yep.
It's much easier to run up
Yep,
each pipe.
absolutely agree. If you see it's cost effective to do distributed units.
Yeah.
Do it. Absolutely. If there's already either an easy path for ducting, or maybe there's ducting in place already
Yeah.
for whatever reason, every project's this individual evaluation on that. But back to flex duct, that's the third greatest invention of mankind.
Well, what about the
It's-
Canadians with their little filled beans that they run
Yeah.
on this thing?
It comes right after WD-40 and duct tape. Yeah. No, flex, you gotta be careful with flex duct. I know it's a problem solver, but have you ever seen flex duct up in an attic where it's been coiled around trusses and people have stepped on
I
it?
love it.
It's got
like track pipe.
very high
Same
static
stuff.
pressure loss. Yeah, it's a Band-Aid. And I know it's easy, but, up here, I should ask you, and I know we're just a little over time, but I gotta ask you some questions here. Do you see bubble foil insulation under heated slabs up here?
On ductwork.
On ductwork, yeah, for condensation control, but nobody is just taking a roll of that shiny bubble foil, picking it and pouring slab. Well, my compliments to you, because we've seen enough of that. It's terrible under slab insulation. Yeah, yeah, and really, it has very little R value.
Yeah.
And it doesn't reflect when it's covered with concrete. Yeah, it's,
Yeah.
lot of misstatements on.
Well,
the
there-
label of reflectix about like what
there is.
is like a magic thing that it
Yeah.
can do. that
It's
it can't
it's been over,
Oversold.
big time.
Um,
Sure.
we're putting in this months ago.
Okay.
A while ago, and, we're putting in a residential air to water system.
Okay,
And we just, we're sort of trying to suss out like, putting in a buffer tank, running heating, running cooling, and like, if you put in a buffer tank and you're heating, like, it's Vermont. Sometimes it's like 40 degrees in the morning,
Mhm.
and then the sun comes out.
Mhm.
It is 70 degrees by the end of the day, and now the house is hot because the
Yep.
sun is hitting the south side. So like, we're having really, really close demands for people who want really conditioned space,
Mhm.
elders.
Okay.
I want cooling, I want cooling right now, I want heating, I
Yep.
want cooling, I want heating, and it's sort of overlapping spaces.
Okay.
And that's not a situation where we're like filling buffer tank for the radiant panel emitters. We're not switching that buffer tank to cooling in the morning,
don't do that.
back to heating.
I'll tell you,
Strategy for that, are we doing direct to chiller heads? In the situation where we're planning to put in a few chiller heads?
there's several ways you could handle it. One way you could handle it if you have simultaneous heating and cooling. And that's,
We're close,
okay, well,
but maybe simultaneous.
all right,
Possible.
if there's a possibility that the client says, I might want to heat this room when it's 20 degrees out this morning, and then I might want to cool this core room where I've got my wine cellar or whatever, right?
Yeah.
Your client says, I want the ability to heat and cool at the same time, 2 buffer tanks. One is chilled, one is heated. And you could use separate heat pumps, or one could take priority over the other. The heat pump could switch back and forth, but it's only capable of so many BTUs per hour. So depending on what those loads are, you'd have to decide, do I want a single heat pump and just toggle it between the 2 tanks with a valve system, electric valve system? Or do I want to do a separate heat pump for heating? You might put a 5-ton heat pump in for heating and a 3-ton heat pump in for cooling, depending on what your loads are. That's one approach. Another approach would be to use really low mass heat emitters like panel rads.
Yeah.
Or fan coils, and then you could switch. But if you wanted to, let's say you did it all with fan coils, so you have very low mass, they could instantly switch between heating and cooling. Back in the mechanical room, how do I want to set that up? If it's going to be a possibility of simultaneous heating and cooling, I'm probably looking at 2 buffer tanks to do that. Depending on zoning and the range of modulation of the heat pump, there is a possibility that you could do, for example, heating through the buffer tank and cooling without the buffer tank. That's another possibility.
Right.
But what you don't want to do is you don't want to heat that tank up in the morning and then suck all those BTUs back out of it to try to do cooling in the afternoon. You don't want to send that thermal mass through that kind of a swing.
So essentially in that situation, we'd be like asking heating to be sitting in the buffer tank and cooling would be direct off the
Heat pump. And the heat pump could be set to maintain a certain outlet water temperature, like 50 degrees. And it'll just modulate. If you had 2 or 3 zones of cooling, and as those zones turn on and off, the heat pump will just, if it's a variable speed compressor, which many of the units are today, it'll just adjust the compressor speed to maintain that outlet chilled water temperature. So there are multiple possible solutions, but you've got to ask the questions up front. Do you want simultaneous? You listen to them, you got to just kind of anticipate, but ask questions. What do you want this system to accomplish? Which is probably an unusual question to most homeowners from heating installers. But honestly, that's where I start. What do you want to accomplish with this? You talk to me for half an hour, tell me everything you want this system to do. probably tell you, yes, we can do that on some of this or most of it, but I'm also gonna be able to say, no, don't do that. I've had people that have 22 rooms in a house and they want a thermostat every room. Can you do it? Sure we can. It's gonna cost $5,000 or $6,000. You're gonna use 3 miles of thermostat cable. And I'm gonna ask you, what do you expect to do with 22 thermostats in your house? Are you really gonna go around and readjust these all the time? Or are you just trying to say, I want this room at 70, I want this room at 68? If that's what you're telling me, I can do that with balancing. I can balance my flows to do that. I don't have to have a thermostat to do that.
Right, you use less than different size.
Yeah. Yeah, so there's a lot of things you can do from the hydronic design standpoint to keep the system simple. We stopped a client once, great client to work for, beautiful house out in Montana. He wanted to do 4 zones of snow melting and the controls were gonna run, just the controls for just the snow melting, we're gonna run $10,000. And I just said, "No, we're not going there." So it's a wonderful field to be in because you can be very creative and you can also really give a very customized solution to your clients. But it's also a field where I've seen projects with basically blank checks and people just load it up with hardware. And
Do you ever see a situation where you would, like, not necessarily, sometimes obviously the systems can provide domestic hot water. But like, say the domestic hot water is like a really high load, and so maybe you don't really want to tax the system with that, well, it's already heating, but it's been a situation where preheat, essentially like, there's a zone that goes to the water heater, like, it's a freestanding water heater zone, maybe it's a heat pump water heater or
Yeah.
fuel source, but like, it gets essentially like a heating zone of its own, where you're putting in a bit warmer water to it, rather than trying to pull it up to 120, 140.
sure,
And sort of reduce the energy
Sure.
cost of that. The system's already running.
in general, the air to water heat pump's probably gonna do better than the heat pump water heater as far as COP
Sure.
goes, especially in the summer when it's really warm outside. That system I mentioned in the parsonage, it's in addition to the panel rads, it uses a TurboMax tank. I don't know if you're familiar with them. They have internal coils that domestic water goes in. And the shell of the tank is the mass of the water. We use that tank as both a buffer for space heating, but also as a preheat for domestic. We're going to heat that tank at most to about 110 degrees for those panel radiators. That's not quite warm enough for the domestic.
But it's a good start.
It's a very good start.
Fantastic start.
Yeah.
It's better than 50.
Yeah. And then that
We're
goes,
in there.
that actually feeds it's a long story, but there was an existing heat pump water heater that was only 2 years old. So we retained it and we just fed the preheat water into the heat pump water heater and topped it off to about 130 in that.
And the pump is on there.
Yeah, yeah.
Probably the half looks to the water heater.
Yeah, so there's all kinds of scenarios like that where, but the guiding principle is always put the heat pump where the lowest water temperature is. Domestic water heating is a really good load for a heat pump because many times you're starting with 50-degree water. So if you're heating a tank as a preheat tank with the heat pump and you've got, 50, 60-degree water coming into it, you're gonna have really good COPs on it. Heat pump's able to run at relatively low temperatures. So, pretty much done here, but let me just see. I put this in as a pep talk. You can read it later. Why is it the best time to be involved as hydronics? There's a lot of very good reasons right now. So I'm very positive, about the market right now. The hydronics market has always been a small percentage of the overall, especially residential HVAC market. I blame that on Willis Carrier. Ever hear that guy?
Yeah.
Yeah, prior to Willis Carrier, most of the houses were heated with, very old but functional hydronic systems, either steam or what we call gravity hot water systems, no circulators. Circulators didn't come into the market until the mid-30s. Prior to that, it was just buoyancy that moved the water through the system. And there's some beautifully engineered systems, no circulators at all. But again, I'll let you read that later. And I also had a slide that summarizes the points here that we've made, again, over time. Here's our website. Not very fancy, but, and we've, just so you know, I've retired from doing design work at this point. I love coming out and doing training programs like this, but, we, got to the point in life where my wife said, you have to drop something from this workload. And I did. We also made this software called Hydro Sketch. You can do the drawings like we had today. I don't know if anybody's tried it. You can go on that website and try it for 30 days. It's $33 a year to subscribe to it. So it's just a palette of symbols that you can drag into a canvas, and then these, what looks like, these are called connectors. They work like in Visio. They change as you move the components around. And textbook, if you want to do a deep dive into hydronic design, there is a textbook out there on that. So I'm very willing to stay and ask questions. Brian, you had a question. I never got back to you. It'll come back.
Go on.
Great. Is anybody else? I'd love to have more discussion.
So-
Okay.
And sort of, I think one of the things moving into trying to do this is sort of running into a little bit of a roadblock, like, who designed it? Right, I feel like obviously you did, but you're tired.
Yeah,
It's a little bit like, there's some skill set within our HVAC professionals themselves. And then to like, we're currently, choosing the space pack product.
Mhm.
And they're like, sure, we give you technical assistance, but like, wait, but the designer's like, I don't want to step on the toes of your HVAC guy. I was like, but you could. But
Yeah.
what you could right now, that would be nice, but then you're at the supply house. And some of our installers are just like, yeah, the guy applied it, they're like, he's just passing the questions.
I feel
along.
your pain.
Well, they seem to have a better technical team
Yeah.
now, because of new technicians, like, that's helping. But it's like, where do you sort of start with like, this is the rough idea, can you tell me like what I'm looking at for a rough design, is that
Yeah.
the technician's the distributor, is that the manufacturing equipment, is it an independent PE? Is it
Yeah.
a more super experienced installer, like our installers done like two, they've done parts of them.
Yeah.
Or like, and as you showed, there are so many different versions.
If you can find a person that has hydronic skills and has worked with hydronics for 10 or 20 years and is willing to work with heat pumps, I will be very frank with you. One of the things we're finding as we've been working with different companies that are doing pilot installations of heat pumps before they go full blown into the market. And depending where they are, they will seek out a local contractor. So they're out looking for a contractor and they'll call. And sometimes what some contractors will do, I can do that for you, but it's going to cost you $150,000 for a residential system. Because I guess they want to either cover all their learning
They're
time,
gonna hire a fee.
or they might, but they're being extremely careful or cautious with their pricing.
Like, I don't know how long it's gonna take
And,
me.
and unfortunately, what this is doing, it's getting a connotation in the market that, look at, these things are great, but they're super expensive. Because we haven't mainstreamed it. Now, if you went out and looked for a source for a ductless mini split here in Burlington, how many companies would install mini splits here in Burlington? 20?
Yeah.
Yeah. So it's an established technology and it's a competitive market.
But isn't that a good question for Space Pack, the manufacturer?
It's an excellent question. And
Puffing up their chest saying, we've been doing this for 10 years. It's
Yeah.
like, well, help us with the design.
well, here's what I've told manufacturers, and actually I'm working with one. I can't tell you who it is right now, but I'll just say next year you'll probably see something from them. What I feel manufacturers should be doing is providing templates. And-
It's like 10 scenarios.
10 scenarios, 20 scenarios. Space heating only, space heating plus cooling, space heating, cooling, domestic hot
Right,
water,
yeah.
radiant floor versus baseboard. 10 to 20 templates that give you the overall layout. Now, what they can't do is they can't necessarily make sure that every template will meet every code requirement in every jurisdiction.
It's also not designed, like you gotta come into your. people
Correct.
Inside.
Right, and
inside
what-
the machine.
This is where a manufacturer is not going to take on the design role for you. They aren't going to tell you, that's a Taco 007 and that's an 1.25 inch pipe.
But at least give the template.
The templates and,
Like, there's a buffer tank.
Yeah.
There's this is the demand, this is the thing, and then I can fill
Yep.
it apart.
so the templates, the piping templates are the start, and then along with the piping templates, this is exactly how you wire it. You have all these terminal boards with all these terminals.
Right.
This is where that sensor goes. Sensor C1 goes to terminal C1 in the heat pump.
Right to the main side, the heat pump sensor itself is doing all of the control work. Like you're telling. me to
It
control it.
depends.
Or
If it's
There's some external.
some heat pumps, many of the modern heat pumps can do, for example, they can call the boiler automatically if they need to.
Yeah.
Can they operate zone valves? Usually not. Usually you're gonna need another Taco box that will do the zoning for you, and then it signals the heat pump to turn on. And again, you've got several companies that can provide that zoning box. So as a manufacturer doing a template, it has to be a generic representation of that. The other thing that I see today, most of the modern heat pumps have extensive firmware, and they have USB ports on them, or they have some type of I/O that can update their firmware. So in addition to providing the templates, so let's say we have 20 templates, okay? And let's say system number 7 is 2 zones of space heating, 1 zone of cooling, and an indirect water heating, okay? So that's system number 7. The manufacturer would provide a thumb drive that would have the instruction settings for the heat pump for every one of the templates. And all the installer has to do is put the thumb drive into the board and say, download number 7. And it sets all the parameters for that with the ability to override. So if it downloads a set point on domestic water for 120 and you want 130, you change it. So that's where I feel the manufacturers need to go for support. They need to create, again, 15 to 20 templates that cover 90% of the common situations. There always is going to be the one-up custom house. You know, they want the pool heated, they want the snow melted, they want the space heat, all this stuff. And Hydronics can do that. And, you know, I've made a living doing design on projects like that. But that it falls between the cracks because the manufacturers don't want the design liability, which you can understand. The wholesalers usually don't want it either. They will guide you. Some of the better wholesalers might have some templates, you know, they might have access to things. But I've also seen really bad advice coming out of some wholesalers, like staple the PEX to the bottom of the subfloor, no plates, that kind of stuff, okay? I think as the market matures, you're gonna see more of the templates and design support.
Yeah.
I will tell you, we desperately need people that